didn't get up at 8 a.m. to come to my review that I worked way too many hours to create, they can go fail the exam. That's probably too harsh. It is 8 a.m. I didn't get to pick when this review happens. But yeah, I have been in Zulansky's lecture every single day this semester, so this review will hopefully be more tailored to his exam than any of the other reviews. So this will be pretty valuable to you, I hope. Well, let's join this Kahoot right here. I've got like 10 questions. They're all about 10 to 20 seconds each of them. I know there's 7 of you, so I'll wait for that last person to join. Okay. Horner's rule is used in string hashing. None of these other rules have names. Who remembers what Horner's rule is? What it has to do with string hashing? Does anyone remember the string? Yeah, yeah. Yeah, I think it is a prime number. Or maybe it's like 32 or something. But yeah, what they do for string hashing is they iterate through the whole string, and then they just multiply each letter in the string by like 32 or some prime number to some exponent that's increasing every single time they go to the next letter. So it's an exponentially increasing number. No, no. I mean, that's just how that's just a string hashing algorithm. Yeah. You could just have a really lame string hashing algorithm that just returns the ASCII value of the first letter, and that would just suck. Because then you'd only have hash values that range from 0 to 256 or something, however many ASCII values there are. This right here is Horner's rule, this property that, so given like in a polynomial like this, a plus a times x plus a times x squared plus a times x cubed plus whatever, you can break that up by just multiplying, by like just putting out parentheses and stuff like that, that just keep getting bigger as you go out. Where else do you see this happening in something that you've seen this semester?
I've seen it in my pre-calc class.
Okay, in your pre-calc class. I meant in this class, though. Something else. There's one other place, at least, where you've seen something like this. Base conversion, yeah. Base conversion is somewhere else that you use Horner's rule. Most of these Kahoot problems are like little things like maybe those last questions at the end that you get extra credit for. Like 6 points of extra credit, right? Every exam has about that many, which is pretty significant. All right, which of the following is not guaranteed to compile? It's this one, the 0B, whatever. Why is that not guaranteed to compile? Yeah, it's non-standard. Yeah, it's not a standard thing in C. It's just that it just so happens most compilers use that. They accept that. And most text editors will highlight it like purple or something for you, a different color. But yeah, if you're doing hex stuff, you can mix and match capital and lowercase letters. You can use a capital X if you want to. This thing in blue, what is that? Is that just 1,473? What is it actually? It's an octal number. It's not base 10, it's octal. When you lead a number with a 0, C knows why would you have led it with a 0 if you didn't mean to do that on purpose to make an octal number. So that's what that makes an octal number. There you go. Oh. Yeah? That means it's octal, yeah. There is no base 4 thing in C, yeah. But I'm pretty sure, because what digits does octal use? 0 through 8? 0 through 7, yeah. So I'm pretty sure if you use a number 8 or greater in your octal string, C will just treat that as base 10, I think. I'm not sure. Maybe it'll just convert it to octal. That might be a good thing to test in code. All right, heap rules. What must a heap be? A heap must be complete. What does that mean? Yeah, so it must be basically full except for the last level, which must be filled all the way from left to right, yeah. And the other things are just irrelevant to a heap. So the complete property is its structural property of a heap. What's the other property of a heap? There's two main properties to a heap. What was that? Yeah, and that's called its ordering property. Yeah. So a heap has a structural property and an ordering property, and it being complete is its structural property. What binary system does C use to represent signed integers? Two's complement, not toes covfefe. This is probably the only problem that I'm going to be going over today that I can guarantee with above 90% certainty absolutely will be on the exam. He loves to ask this question to make sure you know how to spell compliment. All right. So I found this delicious 1.5 pound bag of cereal marshmallows on Amazon. And what is one single marshmallow from this bag called? A Marbit. Do you remember him just briefly talking about this in class one day randomly? Well, he did. And he loves to do little random anecdotes like this as his last problems on the exam. It is not a megabyte, but that would be really funny. If it was like byte, like this type of byte, that'd be a funny name. All right, which of the following is not equal to 0? I gave you a little bit more time on this one. Int max minus int min plus 1. What value is int max minus int min plus 1? What was that? It should be double int max, you think? How can any value in C be double int max? Because int max is the int max. You can't have anything bigger than that. All of these are integers. I'm pretty sure int max minus int min, it loops back around, and it will create positive 2, I'm pretty sure. Actually, now that I think of it, crap. I came up with this at like 6 a.m. today, so this one might be wrong. But this is definitely a good thing to study with, because he could totally give you a problem that's like, create this number, but you can't just write that number. You have to use bitwise operators with int max, int min, and 1. Those are the only things that he would give you at your disposal. Okay. Which of the following is a backtracking algorithm? I gave you non-obvious ones. Quadratic probing is not a backtracking algorithm. That's just going in order through in an array. In-order traversal, though, is a backtracking algorithm, because you go down one branch, and then you come back up, and then you go back down, and you're avoiding previous states, and you're doing a recursive descent, and all that stuff. It is a backtracking algorithm. Pretty much anything to do with a tree is a backtracking algorithm, secretly.
So when you do the binary search, why is that not a backtracking algorithm? Because you go down one tree and you don't find the key, then you go back.
You don't go back up. You've eliminated half of it, and then you never backtrack is the thing. You keep going further down one path. You never backtrack is the thing. So it can't be a backtracking algorithm. You never backtrack. The space complexity of quicksort. That's something new to you, right? Space complexity. It's order log n. Why is it order log n?
Every time it calls the person, it makes one
Mm-hmm.
stack.
Mm-hmm.
That I know that. I know how.
Yeah, so every single time you call quicksort again, that gets put onto the call stack. So that's where the space complexity is in the call stack. So I can see why you would think it's n log n. That's a common answer, because you think like, okay, you're breaking up the array into basically half, and then in half again, and then half again. The breakdown looks a lot like merge sort. And then you've got this thing that's n wide, log n deep. So that looks like n log n, right? But why is that not the space complexity? Does that whole like n wide, n log n deep box diagram thing, does that all exist in memory at the same time at any point? No, it doesn't. At any point in quicksort's execution, you only go log n deep. So the stack is at most going to be full of log n recursive calls. So that's why it's log n space complexity, because you don't have all those recursive calls on the stack at the same time. All right, on average, what percentage of space does a hash table utilize? (25 to 50%). Okay, so most of you got that. I can see why you might think the red one. And maybe that is actually right, like on average, maybe. But
If you use linear probing, maybe you can work out to 15 to 40%.
the probing method doesn't have to do with how much space is being utilized. So you know that the hash table can, at most, use 50% of its space, right? So it definitely can't be up to 66% or up to 75%, right? Definitely can't, because it's at most half full, right? But the reason I argue it's the blue one is after you resize a hash table, how much space is being used? 25%, because it's now, you've doubled it, so it should be a quarter full. So that's why I argue that on average, if you're just keep adding things to a hash table, say, you're going to have about 25 to 50% utilization of memory. But it could be like 15 to 40%, because if you, say you just do an expansion, and now you delete a lot of stuff, and you don't shrink the hash table, then now you've got less than 25% space utilized. Or maybe you just made the hash table and it's empty, and now you're putting stuff into it and it's like less than 50% full. That could happen. Yeah, I think that wasn't it? Thinking about how how can you go below 25%? Yeah. Maybe it's just empty. Or maybe you have a hash table that it doesn't retract, or maybe you've made it smart so that it knows, like, okay, you're adding things. What if you're rapidly adding and removing things from the hash table, and you just happen to be at the mark where you're constantly expanding, contracting, expanding, contracting? That could suck, because you're calling malloc and free all the time then. So, and you're copying things into your new hash table all the time. That would really suck. So you might have a smart thing into your hash table that after you've rapidly contracted and expanded, like within a certain amount of time, it just stops resizing at that point. And at that point, and now you're deleting things that might get below 25% full. That's one of the optimization things to a data structure that he talked about. All right, last question. What's the number 5 on his top 10 places to get yummy food in Orlando? You all probably know the number 1, but what's the number 5? Would he ask that? I don't know. He probably would ask something about the number 1. He does that every semester. The Dandelion Community Cafe, that's like number 9 on his list or something. Yeah. Krungthep is really good. That's the number 5. That would be my personal number 2. It's really good. They don't have a Thanksgiving sandwich, but aside from that, I think everything about them is better than pom-poms. They're just really nice. And that's everything to do with, that's the end of this Kahoot. Let's see who won. It's John. Good job, John. Any questions before I begin with the rest of the review? Okay. So I've had my review posted on my WordPress for like about a week now. Does everyone know how to get to my WordPress? No one ever does. If you just Google UCFSI, you go to the Google and type in UCFSI and hit enter. It should be the first link. This is the SI site for all the SI leaders. If you've got other classes that have SI, you probably do. They've also got their own reviews going on with Study Union. They're all their pages. If you have any of these classes, I mean, this is a lot of classes. Chances are one of you has one of these also. If you go to CECS, Computer Science 1 with Jarrett, that's me. This is my page. These are all the times I had all semester. So these are the times that you could have gone to my sessions and gotten help, but there's no more, so sorry. There's a sweet countdown until the exam, so you could just pin this to your browser and just go to that whenever you feel hopeless. And these are all my reviews that I had previously. This is my review that I'm going to go over today. There's an ominous blank spot here. Who knows what I could put here? Like 10 minutes after this review is over at 10. Like anything could go there, really. Yeah. Any questions? Okay. So these first few questions are, I guess we're just going to have more of a discussion. There's not going to be that much stuff I'm going to write down. So imagine that, so you've got like hash tables, and you could resolve collisions using linked lists, right? So every single index is a linked list. What's that called? Separate chaining. Okay. So imagine instead of having a linked list in every index is just another hash table. Is that a good solution to solving collisions in your hash table? You just get a hash table of hash tables?
It's like a 2D array.
Yeah, then it's like a 2D hash table, right?
Yeah.
Okay.
That takes a lot of space.
It could take a lot of space, possibly. What other issues do you see with doing this? I mean, the benefit is that maybe it solves collisions, you know? It's a way to resolve collisions. Yeah?
Would the second hash table need its own hash function?
Would the second hash table need its own hash function? I don't think so. Maybe just use the same hash value, but now you just mod it by this value of this smaller hash table, right? Okay.
Yeah, I see a problem.
What?
Because, you know, like, if the hash table is this long and each table is that long, what if there's only one spot that has so many collisions and you run out of space in that table?
Okay. Well, maybe you resize that table now. Yeah. But let me ask this. How do you resolve collisions in the sub-hash tables?
I mean, you just keep on adding them, so it's like, to retrieve them, it's like an order n.
But I mean, like, say you've hashed to one of the hash tables. You go inside that hash table. You go to an index. There's a collision.
You will use linear or
linear or quadratic probing. What if inside the sub-hash table, more hash tables? Now it's a 3D hash table. What if there's a collision in that hash table? Now it's a 4D hash table. At what point do you decide to stop? How deep does it go? So this thing is like bringing up more questions than answers now at this point. At what point do I stop nesting hash tables and I just do one of my probing methods? Just don't do that? Okay. That actually is the solution. Because there's another issue with having nesting hash tables like this. It's just the same thing as if you just made the hash table bigger in the first place. If you think about that, imagine you've got your hash table, and each index is just another hash table, right? If you were to go here, and then you just go within here, this is pretty much the same thing. That is an awful arrow. That is the same thing as if this hash table was just absorbed into the parent hash table. Do you see how that's the case? If you just make the parent hash table bigger, it's effectively the same thing. Because if you add up all the sub-hash tables, the number of indices to them, and you just make a bigger hash table with that many indices, you've basically got the exact same thing. You've got, yeah. You'd have to rehash. That could be an issue too. But really, if you had separate chaining with a linked list, right, you would have had to have rehashed those also, right? Because you can't just take your linked list and just point it to a new index in a new hash table, because those values could have hashed to a whole different index in the first place. So no matter what separate chaining method you use, you would have to rehash everything inside the indices anyway, yeah.
So you're saying that we have to rehash no matter what collision resolution?
No matter what collision resolution policy you have, when you resize, you have to rehash everything, yeah. But I guess maybe the benefit with the linked list is you don't have to reallocate all your nodes in the linked list. You can just change the links to them. So you don't have to, so yeah, with this you have to, you're right, actually. You got to free all the sub-hash tables and reallocate new sub-hash tables. With the linked list, you don't have to free all the nodes and make new nodes. You just change the links to the nodes. So that is a benefit to the linked list, yeah. That's a good catch. Any questions about this kooky idea of hashing with hash tables? All right. What if instead of hash tables, having hash tables inside your hash table, what if instead each index is an AVL tree? And you resolve collisions with an AVL tree instead of a linked list? Is that a better idea, worse idea, equally bad idea, equally good idea as a linked list? Each hash table has its own AVL. Each index in the hash table has its own AVL tree. So you go to an index and you just insert into the AVL tree if you're inserting. What's the big O then of inserting into your hash table? Order n log n, where n is the number of things in your entire hash table. So in this case, n is the number of things in your entire hash table. So you go to one index, and you think you're going to do n operations to go through that whole tree, inside of one index? If it's worst case, yeah, you're right. If everything hashes to one index, then your hash table is devolved into one AVL tree. So that would be worst case, yeah. It's just equal to the big O of the AVL tree.
Isn't AVL tree like self-balancing tree? So
Mm-hmm.
if you're inserting, you could just go down one route and just insert it over there. So wouldn't it be already locked in?
I can't remember if AVL tree is n log n or log n. Does anyone know for sure off the top of their head? Log n? Okay, yeah. Yeah, so it's log n in the worst case. It would just devolve into one AVL tree. What about best case of insert?
It would still be log n.
Best case, you think it's log n still? Why do you think it's log n in the best case?
So we have to traverse down the tree.
So you're saying in best case, you have to traverse a tree that has every single node in the hash table in it?
Yeah, because when we use AVL trees, it's not a binary tree. We're giving up our best case.
Mm-hmm.
And because for binary, the best case is always 1. But for AVL, the best and worst are both already log n.
Okay. So remember we've got a hash table where every index is an AVL tree. And the number of things in the entire hash table is n.
I understand.
Yeah.
So if we have a really good hash function, then we don't have to use any other AVL trees. So like everything hashes just fine, and maybe it's just order 1 insertion.
Yeah, yeah. So pretty much always in best case, a hash table is order 1. Because in the best case, you assume you have a perfect hash function, which means no collisions ever. So in the best case, every AVL tree inside this index would have either 0 or 1 things in it. Yeah, so that's the best case. Now what about on average? What do you think this would have?
Order 1.
Order 1? That's what you want with a hash table, right, is order 1? So how would that work? On average, how many things would you expect each AVL tree to have inside of them?
A constant amount, I guess.
Just a constant amount, yeah. If you've got a good hash function, each sub-AVL tree should have maybe like 2 or 4 some things in it. I think that's or I guess less than 20, right? That's like a constant amount. Or even like less than 100. Because then log 100 is tiny, right? That's super acceptable, right? To traverse through a AVL tree, it's got only 100 things in it. Yeah. How does this compare to separate chaining with a linked list? AVL tree versus linked list. Is this better, worse?
I think it's better because, I mean, in the worst case, it would be really better if we assume that our hash function is really, really bad and we have a lot of collisions. This is better because our worst case is order log n.
Mm-hmm.
In linked list, in separate chaining, it could be order n.
It could be order n in the worst case, you're right, yeah. But typically we don't really, let's ignore the worst case then, because let's say we're pretty confident we're not going to get the worst case scenario with our hash function. We got a good hash function. We're probably not going to get the worst case scenario. So let's think about in the average cases for different operations, insert, delete, and stuff like that. So with a linked list and we're inserting, we've hashed to an index. Where in the linked list do we want to insert? At the end? At the head? Okay. Okay, why at the head? Why is that a good idea? It's the policy?
It's like you used data recently, like you probably
That's a good policy, actually, yeah.
if you sign up for something, you get a login right away. So.
Yeah, that's a good example to remember. Yeah. Say you're so the policy is, say you're using a hash table to store login information for a website. If someone just signed up, now you put that information into a hash table. Let's say you put it into a linked list. You're solving collisions with separate chaining with a linked list. If you just put it into the head, the first element, that means that the next time that they look it up, because they're probably going to sign in. They just made an account. If they try to sign in now, it can just grab it straight from the first thing. And that'll be order 1. And that's typically a good policy because recently used data is most likely to be used again. It's a very common policy in computer science. You'll learn that when you do like architecture stuff, when you do architecture classes, yeah. But what other policies could we have with a linked list? The way I see it, there's 3. We've gone over inserting at the head. What other 2 policies might exist? That would be order n, but that's a policy, yeah. Maybe it's a bad policy, I don't know. We could analyze that in a second. What's a third policy that would make sense, do you think? Not inserting at the head, not inserting at the tail. Inserting in sorted order, yeah. So if you insert into the linked list in sorted order, what benefit does that give you? Binary search? Can you binary search a linked list? No, you can't binary search a linked list, which kind of sucks. But think about retrieval. If it's in sorted order now, and I want to search for that element, what's the big O of that? It could still be at the end of the list, yeah. So what's the big O if you're trying to search through a sorted linked list? Order n, yeah. But if we had inserted at the head or inserted at the tail, can we guarantee it's sorted? No. So what would have been the big O of searching through an unsorted linked list? Also order n. But which order n do you think is better? The sorted one. Because actually, if you think about it, on average, you're going to always go halfway through the list if it's sorted. And you can have a cutoff where you know, oh, I found something bigger, it's definitely not in here. In the worst case, it's always going to be order n through a unsorted list. But you could look at the first element in a sorted list, and if it's bigger than what you're searching for, you could just stop immediately. Okay, so maybe, let's say we're going with a sorted linked list then. Because maybe we're not doing a website. Maybe we're doing something, because that recently used data policy, that breaks down like as soon as someone else signs in now, right? They make a new account. Now it doesn't matter that other person was first in the linked list. It's kind of, and maybe if you resize now, it breaks down pretty quickly, actually. At least that example does. So if we go with a sorted linked list, how does that compare to an AVL tree for hashing? AVL tree would still be better. Yeah, in worst case, definitely, because it's log n, yeah. Let's think about best case, then.
Well, still in best case, AVL tree is sorted. I mean, like, when you get into AVL tree and you see the value is, like, bigger than the value you're searching for, because AVL tree, like, it also goes to the smaller side. So, yeah.
Mm-hmm.
Probably for searching, a linked list would be better.
Yeah, because best case could be order 1. It could be the first thing you could cut off. So actually, in this case, a linked list is actually better. There's trade-offs, at least for searching. And an AVL tree is just always log n for everything. But with our linked list, we've got, some times that are order n, but some things that are order 1. And maybe we're doing a lot of searching through this linked list. And if we expect our linked list to always be small, right? If we've got a good hash function that we don't hash a lot of things to one linked list, we expect our AVL tree to be small, we expect our linked list to be small. Order 1 could look way better than log n. Because order 1 could just be one step, but log n could be 2 steps, and that could make a little difference.
Use that logic just whenever we consider big O, like one of the first rules is that we consider everything.
Yeah, but remember the parent data structure is a hash table in this case. So we can consider, if we have a good hash function, then each sub-data structure is going to be really small. If all of the sub-data structures are really big, then our hash table is actually like really filled up, and we should have resized a long time ago. So, yeah, that's a good question to have. But in this case, because we're nesting the data structures, we can consider different cases. Would the space complexity be different between the linked list and the AVL tree? What was that? It would need an additional pointer for every node. So the space complexity would be the same because you're going to have just as many nodes in both. But the AVL tree has an additional pointer in every single node, right? So that could increase, that would multiply your constant by, maybe, let's say your constant you're multiplying by would just be 1 for one pointer. Now you're multiplying that constant by 2. Your constant's 2 instead of 1 because you have 2 pointers instead of 1. So the space complexity is the same, but in the real world, this could take up twice as much space with an AVL tree, which could suck. And these are all like really good points to like comparing these data structures. He could like ask a question like this and break it up into different parts, weigh the pros and cons and stuff like that. He didn't go over nesting data structures that much aside from the separate chaining with a linked list, right? Yeah. I think actually there's one more time that he nested data structures. I don't think he went over it in lecture. I think it was something that happened in labs this semester.
Oh, like even the recursion relations. Oh, that was backtracking.
It was before you learned about hash tables. It was before hash tables where this happens. I guess it's arguable whether it's data structures. It's radix sorts. I think he went over it in lab, is when it happened. Yeah. But yeah, in radix sort, you've got an array where each index is a linked list. And an array is a data structure. It's the first and most basic data structure you learned about, and a linked list is a data structure. So those are nested data structures. Yeah. Any questions about this? Is this like really cool?
So in the end, for like this type of question, based on like everything we just discussed, is the right answer like depending on how you argue it, or?
This would be like a long response question. And I guess this exact question he definitely would not have an exam because he doesn't want to read people writing an essay. But he could pose this and then give you a table that's like big O, insert, delete, search, what is it? He could describe this nested data structure, which I don't think is that like crazy to think about. It's just a hash table where you use an AVL tree instead of a linked list. And he would ask, what's the big O of insert, delete, search now? And maybe he would like, because this is like really broad, we're like comparing all the pros and cons we can possibly think of. He might break it down to just one pro and con. Maybe just the space complexity part. He would ask, how does the space complexity compare? And maybe if you just answer the space complexity is the same, that might just be half points because he's looking for a little bit more. He might be looking for you saying, the space complexity might be the same, but there's an additional pointer in the AVL tree nodes. So the hash table could potentially take up twice as much space. Yeah. Or not twice as much because that would assume every single element has a node in it. More space. It would take up more space. But the same big O. Does that answer your question? Okay. Any more questions to do with this? Okay. All right. So you saw how tries can explode in space complexity because of their array of 26 child pointers. So instead of having an array of 26 child pointers, what could you have instead that maybe wouldn't make your try explode in space complexity? A linked list. This guy gets straight to the the common answer immediately. Right? I don't want to say the right answer because the right answer is debatable, but that's the common answer, as in that's what people actually use in the real world. They don't use arrays of child pointers in the linked list. They use linked lists. That's actually what Microsoft's spell checker uses, is a try where each node has a linked list of child pointers instead of an array. Why is a linked list better than an array for this? You don't have unused space, first of all. So it would take up less space. That's the whole point of this, that it takes up less space. Does this impact the big O at all? How does it impact the big O? What's the new big O? Because the big O of a, so the big O as a try, as you know, as you learned in lecture, what's the big O of inserting an element? Order K, where K is the length of the string, which is like really awesome because at minimum, that's what a hash table would use, right? Because you got to hash the string. So order K is like just the best you can hope for storing your strings. So would this still be order K if you have linked lists instead of arrays? Worst case? Worst case, you think it's still order K? To search through the linked list? Okay, well, let's think about this. How big can the linked list get? As big as it wants? Let's see what someone else thinks. How big can the linked list get? As big as the word? So you've got, so like instead of your array of 26 child pointers, you've got a linked list that will start at 0. And say you insert Zumlansky, your child linked list will just have an S in it. And then the next child will just have a Z in it. And it'll just keep going like that. So each of these linked lists, how big can they get at most? 26. Your linked list is only going to get 26 big at most. So let's say you've got a filled up try that's got these linked lists, and you've got the worst case scenario. You need to iterate through every single element of your linked list to get to the Z, because maybe your linked list is in sorted order. Maybe you need to iterate through this linked list to the Z every single node that you get to. What's the big O of that? You had it right the first time. It's order K. It's order K times 26, right? So you got to do 26 steps to loop through this linked list in the worst case.
If we were expressing the runtime for just searching through the max it can get is like
Mhm.
order 26, which is order 1.
Order 1, yeah. You could say that. I would say, to be more expressive, I would say like order A, where A is the size of your alphabet. So in this case, we have an alphabet of just size 26, just A through Z lowercase. But maybe you've got a way more complicated try that accepts capital letters, hyphens, commas, apostrophes, stuff like that. Maybe it accepts every single value a char can have. So, and you can have bigger alphabets than that because there's like umlauts and stuff like that, like O's with little like 2 dots over them and stuff like that, N's with tildes. So you could have a really big alphabet. So I would say that just the linked list could be come up with a new variable, order A, where A is the size of your alphabet. So what does that now make the worst case of your inserting a word? Order A plus K? What if, I mean, every single time you get to a new node, you might have to go through that linked list. So you go to K nodes, and for every K node you visit, you have to go through a length A linked list. A times K. So you're doing, because you got K letters, and each letter you might have to go through a linked list of size A, which could suck. But that could still be like really small, right? Maybe you've only got 26 letters. A is going to be limited to probably something less than 1,000, right? So that could be not that terrible in the worst case. But what about on average? Do you think most of these nodes are going to have a huge linked list? Can you say with certainty, though? Can you say with certainty that most nodes aren't going to have a huge linked list? What does it depend on? Your corpus. I'm glad you used the vocabulary word. It depends on your corpus. If your corpus is like the English language, honestly, I feel like most nodes aren't going to have a huge linked list. Most nodes, like towards the top, are going to have a huge linked list, right? But then as you start branching out and getting down to words that have less things in common, your linked lists are going to get smaller. And eventually, you probably won't have to iterate through any linked list as you get further down. Yeah. So I would argue on average this could still be order K. But again, that depends on your corpus. And you have to do like a statistical analysis on your corpus to see how similar all your words are and stuff like that, and it gets really complicated. Any questions about this? Yeah?
What do you say the worst case would be 26 times? Like, I didn't get that. Like,
Okay, so the worst case, you've got every single node has a linked list of child pointers. The worst case, to get to a node's child would be going through the entire linked list, right? The linked list is going to be at most size 26. A through Z.
but
Children A through Z.
if you insert Shumlansky, so like, there are like 2 S's, I think, and it's
Uh-huh.
S is counted twice, so that's how it works.
Well, you'd go through the S. Well, the other S would be at a completely different node. Yeah. Or what if you're not inserting Zoomlansky? What if you're just inserting a bunch of Z's? That's your string. It's someone snoring. So you have to go through the entire linked list for every single node to get to the Z. Yeah. Does that answer your question?
So the runtime would be order K for insertion.
I would say on average, if you've got like a a not crazy corpus. If your corpus is full of words that have nothing to do with spaghetti as their prefix, then that might be like really bad. Maybe even your linked list isn't sorted. If your linked list is sorted, then you could have that advantage that sorted linked lists have where they could cut off early. But if your linked list isn't sorted, it could just be really sucky, and you might always have to go through to the last letter all the time. But again, it all depends on things that are like non-deterministic to do with the algorithm of the data structure itself. It depends on your input and how weird and different it is. Tries get really complicated when you observe their complexity in different ways. And Zumlansky loves tries. He will probably have a question or two on tries on your exam, for sure. He loves tries. Any more questions to do with this? Is it like really cool and eye-opening that this is what people do in the real world with tries? Okay. All right. How would you go about creating a mid-heap? So you know how to make a min heap, and a max heap is really easy. You just flip your less than sign to a greater than sign in your code, and now you've got a max heap. How would you make a mid heap where the root has the mid element?
Isn't that just an AVL tree?
An AVL tree?
Yeah, because the root of the AVL tree is exactly half.
Oh crap, you might be right. I didn't think about that. Maybe an AVL tree is a mid heap. Or a binary search tree? Well, a binary search tree, it could have devolved into a linked list or something, right? The first element could be who knows what. The first element of a binary search tree is the first element you inserted. And that can't be guaranteed to always be the mid element. But yeah, maybe you're right. And I didn't even think about an AVL tree being a mid heap. Because it always balances. You're right. That might be it. Okay. That wasn't the solution I was thinking of, but we'll compare that to my solution. So if it's not an AVL tree, how would you do it? What was that?
So if we have like a short array, we'll take the middle element of the root and then we'll break like from the 0 to the mid minus 1. We make it equal to the left of the root and we make the mid plus 1 to the end of the array equal to the right of the root and then we do it recursively.
Okay, I think you're close. We will use arrays. We are going to store our data into arrays. And I like that you've bisected half of it to be larger and half of it to be smaller. And that might actually be more, there might be something to your idea to make it like slightly more efficient than my solution. I'm going to let you guys stew for just a little bit longer. I want to hear like at least one more idea before I give it out.
Could you insert, because heaps are like arrays in here,
Uh-huh.
could you just insert it in sorted order? Because you would know where your last node is,
Mm-hmm.
so you would just increment it by 1 to account for your newly sorted,
Okay.
and then just take that number, divide it by 2, and like pick a 1 higher, 1 lower if it's odd.
Okay.
Because that'll get you the index in the middle of the array, and since it's sorted, that'll be like, the only time you'd have to like choose 1 higher, 1 lower is if it's like an odd, you get like a point.
Okay. Well, problem with that is if you insert like into the middle, now you've got to shift all your elements one over, right? Or I guess this way because you're looking at me the other direction. So if you insert into the middle, you've got to shift all your elements behind it over, and that would be an order n operation. And we want heap-like runtimes. We want similar or same runtimes as you would get with a normal min heap or max heap. Did you have something? Okay. Any more ideas? Yeah? Yeah. What if we just have two heaps? We have a mid heap and a max heap, or a min heap and a max heap, and when we insert, we just, is this less than or greater than our mid? Okay, I'll just insert it into one of those two heaps based on that. And then we just look, and then when we want to get to the mid or the mid, we just compare the root of the min heap to the root of the max heap, and we just have a policy. We just grab maybe always from the max heap. Actually, yeah, we don't need to compare. We just would always grab from the max heap, maybe.
So the left child of a root would be the min heap.
There wouldn't be a root. We would just have a struct that has two heaps in it, a mid heap and a max heap. We would literally just have two heaps, and we just pick which one to insert into based on whether this value is greater than or less than our mid, which we could just say is the average, maybe just the average of the two heaps, two heap roots. But yeah, that's how you would make. That's how I would make a mid heap. All right, let's compare that to an AVL tree now, because an AVL tree is maybe just an even easier solution. I can't believe I didn't think of that. If you think of a solution that is like rock solid that Zulansky didn't think of when he created the exam, I think he might just give you an automatic 100, because I think he should, because that's amazing, coming up with something that he didn't think of.
Yeah, that's impossible.
It's impossible. That's impossible. That won't happen.
The guys over there, doing the exam like 10 times.
Yeah, he's been thinking about this exam since,
The semester has started.
yeah, he's always working. Right now he's probably thinking of the first assignment for next semester. Actually, no, he's probably not doing that. He's probably been up for the last 48 hours writing this exam. Okay, so let's compare AVL tree to having two heaps. Let's start with space, talking about the space. Is the space complexity of one worse than the other, or are they the same space complexity?
The AVL has, in like order, big O like kind of notation.
Uh-huh.
It has kind of one, well,
In space complexity. We're talking about space complexity right now.
both of them.
And for both of them. They both have the same space complexity, but let's try to think slightly more real world. Is one going to take up a little bit more space than the other? What was that?
The mid heap has like twice space as the normal heap.
Mhm.
Like in a struct you have like a min heap and a max heap.
Uh-huh.
So it's gonna take like twice space as the normal one.
Yeah, okay, so compared to a normal heap, a mid heap would take up more space because you got to have references, you got to have a struct, you got to have references to the different heaps. So that would take up some space, yeah, a little bit more space. Let's compare our mid heap to an AVL tree.
Each node made with arrays, the AVL tree with structs.
Yeah, so the AVL tree's got nodes, the other one's got arrays. And you were about to say something about the nodes.
Yeah, the nodes for like the min heap and the max heap are like identical, or not the min heap and max heap, the AVL tree. And
Uh-huh.
the heaps.
Uh-huh.
So you wouldn't have to like worry about the 2 pointers like left and right. You just
Yeah.
it would basically just come down to the struct.
Okay. How about this? So the AVL tree, all the nodes have pointers and stuff, right, to their children and stuff like that? That takes up space, right, those pointers? But in the heaps that are stored in arrays, those are just arrays. Those just have the data in them, right? There's not 2 pointers for every single piece of data, right? So which of the two is going to take up slightly more space?
The array because of wasted space.
Actually, yeah, you might have a point. The array, that's another thing to consider. So assuming the array doesn't have wasted space, the AVL tree will take up more space because each node, for each element, you've got 2 pointers. But the heap that's got arrays, at the same time, the array might have wasted space, yeah. I think a good policy for a heap you could have it expand like a hash table. Once it gets half full, you resize it. Actually, no, once it gets completely full, you could double it, is a thing you could do with a heap. You could also use those arrays that you made at the beginning of the semester, right? What were those called? Listy strings? Or listy array? What were they called? The lonely party array. Yeah, you could make your heap out of lonely party arrays. That's something you could do. But then your lonely party arrays might have slightly wasted space, right? But at least that's a fancy way to have them expand and stuff like that. So yeah, if he were to, maybe he would present this. That could be a question. He could present this, comparing this design for a mid-heap versus just an AVL tree. Compare the space complexity. And he would probably look for 3 points, recognizing that they're both order n, recognizing that the heap with arrays could have wasted space in the arrays, and recognizing that the AVL tree nodes have 2 pointers each, and that takes up space. And yeah, so that's space. Runtime, is the runtime the same? What's the big O of a heap again? Log n for a heap, yeah.
I mean, like, to delete or to insert? Oh, it's the same.
It's the same, yeah. What's the big O for an AVL tree?
Log in.
Log n. So they both have log n runtime, which is pretty sweet. And I don't think there's anything more to say about the runtime than that. Any more thoughts on this?
So the space complexity, if you made a struct and had only mid-heap and backheap in it, so that would be less space complexity compared to an AVL?
They both have the same space complexity as order n. I think just having that one parent struct that just references a mid-heap and a max heap, that's such a small amount compared to, say, how much data each of those arrays has. It's such a small amount, it's not even worth considering. But the big points is that the arrays could have wasted space, and the AVL tree, each node has pointers, and those take up space.
Yeah, so when we create the heap, we have to determine the capacity that it can.
You might have to. Maybe your heap has a max amount. That could be something that you want in your algorithm that you're using your heap in.
I think he had integer.
Yeah, you might need an integer capacity and size. And I don't think that would be an issue with the mid-heap because you would just have the capacity and size of the parent, the mid-heap, and then each sub-heap would just need to be half that. You wouldn't need to think, does one need to be bigger than the other? Because each should have roughly the same amount of things in it, right? If this is the mid, there should be half things in one heap and half things in the other heap. So each heap would just need to be half the size. Yeah. Or you could just have the arrays expand. They could be lonely party arrays. So there would be no capacity or max size to your heap then. Any other thoughts or questions on this? Okay. All right, that's, I think, the end of my questions that have to do with, like, conceptual nesting data structures and stuff like that. So let's get to some actual code. So I've got this function named wonder, and what would be the output, because it's going to print some stuff, if I input an array that has strings Dick, Jason, Tim, and Damien? What will be the output? let you look at this for like 5 minutes or something. Who came in recently that didn't get a survey? There you go. There you go. Anyone else? Everyone's got a survey? Okay. Yeah, like 10 minutes after this review, I'll post the answers. Okay. Okay, who has an idea of what this thing will print? Yeah?
I don't know, maybe I got this wrong, but it looks like the J is going back and forth between 0 and 1. So it's only going to print the first two names.
Okay, so you think the J is going back and forth between 0 and 1. Okay. So you think it'll only print the first two names. Okay. Any other ideas of what it'll print? Because it's gonna print the names, yeah. So I guess more specifically, like, how, in what order is it gonna print them? It's got these curly braces and stuff going on too. Let me ask this, is anyone taking discrete 1 this semester also? 2 people taking, 3 people taking discrete 1, 4 people taking discrete 1 this semester as well? Okay, you people probably have a advantage on this problem, because this is doing something that you learned about this semester. I love discrete. That was my favorite class to SI for. That's the first class I SI'd for. Yeah? Is it just printing out the array?
No, I mean the first index of the input inside the parentheses.
Okay, it's gonna do that at some point, yeah. The first index. Let's trace through this a bit. Here it is. Okay. So we've got we're passing in the array, its length. We've got 3 variables, I, j, and m. M, I guess I could have named this n. I don't know why I named it m. Oh, because this was originally n in my original code. Okay. So m is equal to 1 shifted to the left by the array length. So what does that effectively do then? What number is this in like math? What was that? 16? Oh yeah, I think it is 16, you're right. In this case. Okay, but in terms of the array length, 2 to the power of array length is what this is, okay? 2 to the power of array length. I'll just say this is 2 to the n, basically. So we're going to loop that many times. So the big O of this function is at least 2 to the n, which is kind of big. Then we print a curly brace, all right. All right, then we have j equal to 0, j is less than I, which is currently 0. So this function, this for loop isn't gonna run the first time. So we just printed a closed curly brace. Those of you that are in discrete, there's a reason I picked curly braces. Next iteration of the loop, I is now going to be 1. So we're going to loop just once. If I shifted to the right j times, so right now I is 1, and we're shifting it to the right j times. We're in the first iteration of this loop, so j is 0. So we do nothing to I, basically. And we're going to AND that with 1. So I is 1. Shifted to the right by 0 is 1. So 1 and 1 gives us 1. 1 bitwise and 1 gives us 1. If 1, which is true, then we're going to print j. And j is 0, the first element, dick. Okay, so we print dick. And this loop is only going to go once, so we get out and we close the curly brace. Okay. Next iteration of the loop. J is 0, j is less than I. So now I is 2. So we have 2. Yeah? This is going to print all subsets of the input array, is what it's going to do. That's what it's going to do. It's going to print all subsets of the input array. So if you think about this, I'm going to write out I to the side right here. So in this first iteration of the loop, I is 0, 0, 0, 0. In the second iteration of the loop, I is 0, 0, 0, 1. Actually, my bad, it prints Damien first. Or wait, does it? Hold on. I might have done this backwards. In the second iteration of the loop, it'll print Tim. Do you see how this is going? These here corresponds to like 0, 1, 0, 0 up here. So we're using this integer, just I, to represent which of the indices from the array we're going to print out. Pretty nice. This was actually a problem on my foundation exam. So this is like hyper relevant to all of you. Is everyone here taking the foundation exam? Okay. I would just study for the foundation exam. Don't study for this exam, study for the foundation exam. Because the foundation exam is going to be harder than this. If you're ready for the foundation exam, you're ready for this exam. And I'm pretty sure Zoomlansky helped write the foundation exam. So, yeah. You think so? Some people say that? Well, some people are always going to say that one exam's harder than the other, yeah. But the foundation exam, I think, has like a 50% pass rate. 55? So it gone up? Okay. Oh.
I thought that's what you said.
No, I said 50. I'm pretty sure it has like a 50% pass rate on average. And I don't think Zoom Lansky's class has a 50% pass rate. I think it has higher than that. When you don't account for the people that dropped out. If you account for the people that dropped out, I think most people do not pass this class. Any questions about this problem? Okay. And this is like the most efficient way to generate all the subsets. This is how, if for some reason you need to generate a subset in code, this is how people in the real world do it. Okay. So I've got code here. What's the big O space complexity of it? Going over a lot of space complexity today, because that's something that you didn't cover a lot in lecture, but I have a strong feeling he will ask that on the exam.
About the space complexity, but the runtime is really bad because we can't string length all the time.
Oh yeah, it's not good. But we're not worried about this time complexity, just the space complexity. Yeah. I wrote this function with the names that I chose because I'm like really excited for a movie coming out next year. Yeah, Godzilla. It's got King Ghidorah in it. It's gotta be good. It's gotta be good. Oh yeah, Mothra's also gonna be in it, and also that pterodactyl guy. I forgot his name. What was that? Rodan. Yeah, or Rodan, however you say it. He's gonna be in it. That's gotta be good. I mean, Kong Skull Island sucked, but I'm hopeful for this one. The runtime's really bad, but the space complexity is also not great. No, I'm not. It's got massive memory leaks.
I feel like if we showed this code to Zelensky, he would be like, okay with it. Like, just looking at it would bother him.
Oh yeah, I mean, it should bother anyone that looks at this code. Yeah. It should make you like massively paranoid. What was that?
You're ignoring the return value of malloc.
Oh yeah, I'm not even storing the malloc anywhere. I'm just calling it. I'm not even capturing it at all. I don't even care about the pointer that it made for me. I just want this thing to take up space. So it's taking up space from malloc, and it's taking up space from the recursive calls. There's two places that I'm taking up space here. Like 2 places in memory. It's taking place on the stack and the heap in my RAM.
But I don't know how to figure out divided by 3 every time.
Mm-hmm. So if you look lines 11, 12, and 13, what is happening there? I'm doing Ghidorah plus string length over 3. What's getting passed into the next call of the function? What was that? Some random address? Not random, but it is passing in an address, right? Because it takes a char star. It does point to something, but it's not random. What are you looking at? What are you doing? Okay. Boosting my views. So if we take the address that Ghidorah is at, yeah?
I'm thinking the first time we're creating an order n space, calling them out in kind of order, and then
Okay.
we're placing an order n call stack, order n call stack, and order n call stack, which will all like become order n times order n times order n. Like,
All right. Well, the call stack isn't going to be order n, but you're right about the loop being order n, yeah, because you're looping n times calling malloc for an order 1 thing.
Are you doing pointer arithmetic?
I'm doing pointer arithmetic for sure on lines 11, 12, and 13, yeah. I could have achieved what I'm doing on those lines using square brackets and ampersands, but I chose not to because I'm an elite computer science programmer, and I want to use pointer arithmetic in C because C lets me do that, and it's really cool. So if I take the base address of Ghidorah and I go up by, am I going to the end? Plus string length. If I was plus string length, I would just go straight to the end, right? But I'm dividing it by 3. So I'm going up by 1/3 of the string every time. Yeah.
Would it be logarithmic?
It's going to be logarithmic stack complexity, whatever. So you straight up can't solve this problem in your head. If you can, you're like a genius. We've got to do some math on paper here. We got to use some recurrence relations to analyze the space complexity. The tip off to that should have been that it's a recursive function. So you've got to use recurrence relations to analyze the space complexity. On the exam, well, you had to do a recurrence relation on one of the exams, right? Yeah. So we could totally ask you to do. Wouldn't that just totally be super mean? Like, hey, remember recurrence relations? A wildcard question? Yeah, possibly. I mean, this is a recurrence relation to do with space complexity. That's a combination you've never seen before. But I think it's totally acceptable for him to expect that of you because you know space complexity, you know recurrence relations. He can expect that of you to just put 2 and 2 together like that. Maybe not an example as like mean or complicated as this, but I mean, if you're prepared for something worse than what's going to be on the exam, then you're ready for the exam, right? That's how I study. Okay, so let's look at this. We've got a recurrence relation. What's something that we need for a recurrence relation? We need a base case. So let's say t of 0 equals t of 1. This is how I like to do my base case, equals 1. And this is the base case. When we've got a, I guess this should be not 0, but 1, actually. You return. That's just constant time, right? Why should this be 1 instead of 0? For the null terminator? Not quite. So let's look at this. Towards the end of the array, we're dividing by 3. Let's say I have an array of length 1, right? I've just got 1 character left in my string that was passed in originally. I get the length of that, it's just 1. I divide it by 3. What's that as an integer now? 1 divided by 3 is 1? 0. So I'm adding nothing to this string here. So I'm going to do a recursive call now, and it's just going to do that again. I'm going to infinitely recurse now because I'm not moving up at all. But now that this is looking for 1, now I know if I have a string length of 1, it'll stop. So that's good. Okay. Now in order n, in a length n here, we're doing n spaces we're taking up. Cool. Plus we're doing 3 recursive calls, where we pass in roughly n over 3. 1/3 of the size of the array, because we keep bumping it up every time. Now this is a recurrence relation that I think you can solve, right? Is there anything missing from this recurrence relation? Yeah? Actually, I think you're right, 2n over 3. How about if I solve that problem by doing this? Just multiplying this by 2, yeah. Good catch. Okay. So if it's 2 times string length over 3, now this recurrence relation matches. There's still something missing from this recurrence relation. For n greater than 1, you gotta have that. All right, I don't have enough space to solve this on this page, so I'm gonna go back here. Okay. All right, well now we're just gonna do some nesting here. So this is plus 3n plus 3t of n. Nope, not n, my bad. N over 3. N over 9. Does that step there make sense so far? Okay, I'm going to keep going. Okay. So who can see a pattern so far? Where we put this in terms of n and k. Yeah, this becomes, this becomes n here. This is 3 times n over 3. This is 3 times n over 9, which is 1/3, times 3, which becomes n again, plus 3 times 3 times 3. We need to turn this into terms of k still. So remember, this is like this is still k equal to 3. So in terms of k, we're like k levels deep of calling our recursive function, our recurrence relation. In terms of k, what is t of n? That's the next step. We've got to work k into this equation, and then we're going to replace k with something in terms of n. Not quite. Do you have something? Okay, I think you have it, yeah. So we have, if k right now is 3, this is k n's right here, right? If we were to go one level deeper, we would have had 4 n's. So this is kn plus 27. That's 3 to the 3, right? That's, if k is 3, then this is 3 to the k. T of n over 3 to the k. So that's that in terms of k. Now, this t of n is annoying because that's how we got here in the first place. We kept trying to substitute t with something by going deeper, but we can't. If we just keep doing this, we're just going to keep having a t. So to get rid of this t, we've got to replace it with 1. And the only way we can do that is if we can get n over 3 to the k equal to 1. So t of n over 3 to the k equals 1 when n over 3 to the k equals 1. So let's solve for k in terms of n. What should the next step be? Algebra. So what's the first algebraic step? Yeah, multiply by 3 to the k. What's the next algebraic step? Log base 3, yeah. And that's k, log base 3 of n. So I can substitute that in. And I've got n log base 3 of n plus 3 to the log base 3 of n times t of 1. This is n log base 3 of n plus 3 to the log base 3 is just n plus n. So what's the big O? N log n. So the space complexity actually isn't that awful. It's only n log n. I mean, it could be better, but I mean, it looked like it was going to be like 3 factorial or something awful, or that, no, 3 factorial is just 6. It looked like it was going to be like n to the third or something terrible like that, right? It's just n log n, which could only be like maybe n times something that might as well be a constant, right? Because logarithmic makes things really small anyway. So it's not that awful. It's still worse than the space complexity of quicksort or merge sort, right? But for a function that does nothing, it's not awful. That is still an n log n memory leak that you've got. Any questions about that? Okay. I have one problem left. It's just a pretty basic try problem. So I've got to try. I guess I'll zoom in more for you. I've got to try. What strings are in the try? What was that? Yeah, got the empty string. Don't forget that. We've got one empty string right up here. What other strings are in the try? This one? This is an X. Yeah, sorry. X. Xenon. We've got how many xenons? We've got 3 xenons. We've got 1 xenophobia, or one xenophobe. A xenophobe is someone who's afraid of the outside, in case you were wondering. Two xenomorphs. What is xeno? What is xenomorph? Okay. We're going to insert something into the try in a second that might give that away. We have 5 xenomorphs. If you got 5 xenomorphs, that's a bad situation. I'll tell you that right now. Okay. So now we want to let's insert something into the try. Let's insert Ripley into the try. Where does Ripley go? At the root, yeah, because we've got no other strings in common. So let's put Ripley would go, the R would go over here. And at this point, we've got a completely new branch, right? So it's going to be really easy. I, P, L, E, Y, Ripley. We have 1 Ripley. Is it obvious what a xenomorph is yet? The xenomorph is the scientific name for an alien, like from Aliens. Like the black alien that's got like a mouth and like the face huggers. Yeah. You haven't seen that? That's like my favorite movie. It's a great movie. All right, so we have 1 Ripley. Let's insert xenons. So like xenon plural. Where would that go? Right down the middle. All right. And let's insert xenophobia. I, A. 1 xenophobia. Great. Let's delete something now. Let's delete let's delete all our xenomorph. Let's get rid of all these bad aliens that will kill people and do bad stuff. Let's get rid of all our xenomorphs and other xenomorphs. What will the try look like after that? You won't have this branch at all. Because you just delete this node, and you recursively go back up calling delete node. Yeah, that's what'll do it. Any question about tries, inserting into a try? This is, I hope, like a really obvious exam problem. He just gives you a picture of a try and tells you to draw what it looks like after you add some stuff and delete some stuff. Yeah?
So the reason why we inserted Ripley in a different branch is because the first letter we saw was X.
Yeah.
So if that branch had an R, like in a different branch, then we would go down that tree.
Yeah, we would just go down that tree. Maybe we gotta insert like Xeno Ripley, like Alien 3. Spoiler for Alien 3.
And then my question is, if there was a word called bread in the try, we wouldn't make a new bread.
Okay. Everyone good on this? All right. I have no more problems prepared. So do you have any questions or problems, like, in general?
On exam 2, he put kind of like the traversal output for like a binary tree or search
Oh,
tree.
like an in-order or post-order
Yeah, can you just
traversal?
walk through the logic on how we find out like if it's post order, in order?
Okay. Yeah. I think I have a problem like that on one of my past reviews. Oh, maybe I don't. Oh, I do. Okay. Yeah, I have a problem exactly like that on my exam 2 review. Okay, so if you go to my exam 2 review, here we go. I've got exactly one of those problems. So I've got pre. Eight, 26, 72, 63, 69, 79, and 98. Okay? So looking at this, also an important piece of information that was given here is that it's a binary search tree. Not just that it's a binary tree, it's a binary search tree. Okay. So you've got a pre and post order. You should be able to instantly tell me what the head is right now, what value is at the root. 97? Yeah, 97's the root. Because pre-order, the first thing that'll print is the root. And the post-order, the last thing it'll print is the root. All right? So let's start with 97 as our root. All right, done with 97. Now we've got 46. And if we're going in pre-order, the next thing that'll get printed out is over here, 46. 43 goes next. 8 is just right over here. Now 26, okay. It wouldn't go to the right of 43 because it's less than 43. So it must go to the right of 26. So far this pre-order checks out because you're just going down in order, in the order that you visit the nodes. Next is 72, which is less than 97, greater than 46. '63, 69, again, so far this checks out with the order because pre-order is going to print out the nodes in the order that you visit them in. So 97, then 46, 43, 8, 26, 72, 63, 69, 79, and then 98. Was that straightforward, and are you good? Okay. Any other problems in general in all of Computer Science 1? Or possibly on the foundation exam? A geometric sum? Oh, crap. You think those will be on the foundation exam? Sums? I haven't seen them on the foundation exam before.
That's what we're looking like. It's like really because of the review material.
Uh-huh.
It's all over the place. Like looking.
Really? Okay.
There was, I know we covered it in labs, not in lecture. There was how you parse like mathematical like statements, like you put them onto a stack. It's like postfix or prefix or whatever.
Uh-huh.
There was all kinds of stuff on there. So.
Okay. Yeah, I guess there could be a geometric sum. I was really thinking of putting a geometric sum in that space complexity King Ghidorah problem I had. I guess he could do that, sure. He could have if he's going to do it could be a recurrence relation with a geometric sum. Could be really nasty. Okay. What does a geometric sum look like? It's like 2 to the something, right? Okay. That's geometric, right? Yeah, 2 to the I. Okay. This is where you do the zaps, right? 2 to the 0 plus 2 to the 1 plus 2 to the 2. Okay. So there are formulas for solving geometric sums, but you didn't learn those. So you get to do it this way. So the key to doing geometric sums is just considering this whole sum as S. And now 2S, just multiplying this by 2, would give you, so 2 to the 0 times 2 is just 2 to the 1, right? So if you just multiply this whole thing by 2, it's basically like you just shift it up by 1, is all that happens. And now, if you do 2s minus s, 2s minus s, now this comes the fun part. Are you going to say it? You guys promise to say it when I do it? You guys suck. I'm not even, this session's over. Kidding. All right, zap, really boring. And then you get 2 to the n plus 1 minus 2, and then there you go, big whoop. Your big O is order 2 to the n now, right? Is that correct? I think so. Yeah. Now you've solved the geometric sum. Cool? Okay. I'm really disappointed in all of you for not zapping with me. All right. Any more questions? We have 4 minutes.
I know, like, he says everything we covered in, like, lecture and labs is fair game.
Yeah?
But since we covered, like, the postfix and prefix stuff, like, I remember it in one lab, I think it was right after exam 1.
Mm-hmm.
Do you think that'll be on there?
Well, postfix and prefix stuff.
Not, like, incrementing, but, like, where you're, like, pushing stuff onto a stack, and whenever you, like, hit parentheses or something like that. Or infix and suffix or whatever it's called.
Oh, yeah, that postfix and prefix notation, yeah. That was since an exam, right? That was since an exam? I thought that was before exam 2.
Being in a lab and not a,
It was in a lab, yeah. I don't think he'll test you on that. That used to be something that he really liked to test. I definitely had that on one of my exams, but I don't think that would be on an exam 3 thing, especially since it was a lab. But, I mean, that is fair game, you're right. That could even be on the foundation exam. It's like a really classic computer science problem. I would say it's probably going to be mostly stuff since exam 2. Like he gave that, he had like a little survey in the last lecture, right? Or is that CS1 or Intro to C he did that? You guys don't remember him giving a survey? Okay. In Intro to C, he gave like a little short survey, and he was like, because in Intro to C, what they've done since the last exam is memory allocation and pointers, which is like instructs, which is like a big deal compared to if statements and functions, which is what they were learning before that. So he gave like a little survey. Do you want it to be mostly stuff since the last exam? And no one raised their hands. Do you want it to be even stuff from the whole semester? And everyone raised their hand because they wanted as least amount of structs and pointers as possible. But he probably won't do that. He's probably going to give them mostly stuff since the last exam. Because all the exams are weighted evenly, right?
No, the final is
Like
5% more.
Okay, actually that makes sense, I guess. But yeah, it's probably going to be mostly stuff since the last exam. Any more questions? We have 2 minutes. Any dying questions to do with computer science or the foundation exam? No more questions? You're just totally good? You're totally going to ace this exam? No question in mind? Or are you just ready to go back home and go back to bed? Okay. All right, well, thanks for showing up at 8 a.m. and sitting through my review that I worked so hard on. Thank you. Because it's 2s minus s. So everything canceled out except for the thing at the end of 2s and the very first term. Oh wait, no, it's -1, not -2, because it's 2 to the 0. Yeah, you're right, my bad. Thank you.